So I'm very, very happy to be able to introduce Professor Cherie Kagan from the University of Pennsylvania. Cherie is and let me get this right, the Stephen Angelo Professor of Electrical and Systems Engineering, and also has appointments in a couple of other departments, material science and chemistry. She's really an expert in biochemical and chemical sensors, but she also is the PI of an NSF Engineering Research Center led by Penn called IoT4Ag. And in fact, her team and the IoT4Ag Institute has been doing a pretty broad range of research activities that have strong overlap with some of the things that we are doing here at Illinois in the Center for Digital Agriculture, and also more specifically in the AIFARMS AI Institute. And so I'm very much looking forward to this talk. In fact, I've been wanting to host this for a long time, so I'm very glad you're here.
Thank you. Well, I wanted to thank you, Vikram, and Jessica for arranging and hosting my visit. It's really a great pleasure to be here. I think there are lots of synergies, as you mentioned, in the kinds of work. And it's such a big problem. I think it'll certainly take at least all of us to be able to make an impact that we want to in this space of thinking about precision agriculture. So I'll start. I'll introduce a little bit of the center, and then I'll focus a little bit on one aspect of the center, the part that I know better, as well as I go through. So I'll just introduce you to, so IoT4Ag is one of the NSF Engineering Research Centers. And so unlike, I think, the AI ag components that you guys are part of, I won't say we're the only one in the ag space. There's a new one that's looking at fertilizers, I think, that came in the class after ours. But there's lots of different topics for the NSF Engineering Research Center. So we as a group decided and came together around this idea of the applications of technology in looking at the space of agriculture. And so you may know, and I'll introduce you as we go through, to lots of my colleagues. Apologize for my spelling mistake. That's my own fingers here. Not intentional. I just looked at it and saw it now. But you'll see, and I'll introduce you to many of our colleagues. We have 4 universities that are sort of core partner universities that are part of IoT4Ag. In addition to Penn, it's Purdue University, who you guys probably know very well. They're not too far from you. The University of California at Merced, and the University of Florida. And so we come together, and I'll tell you a little bit about the aspects of the Engineering Research Center as I go through perhaps the next couple of slides. So we have a mission. It's probably not so different. I didn't bother with our vision. I think they probably would look the same. And so we look at, as our mission is around the idea of precision, of creating and translating into practice Internet of Things technology for precision agriculture. It's probably not so different from yours. We focus only to date on crops. We haven't yet dared as confidently to bring on animals yet, even though that's the one thing that Penn has is a vet school that's very big. So you can think about the amusement in that. And then, of course, is to train and educate a diverse workforce that will address this societal challenge of food, energy, and water security. And so you'll see I won't talk about some of the other programs as much in detail. Jessica and I got to sit on a panel together some time ago talking about ag at the FIRA conference. But one of the things that, as part of an engineering research center, is that in addition to our research, there's sort of core directions in workforce development, diversity and culture of inclusion, and innovation ecosystem. So we do actually formally have, as part of our innovation ecosystem, membership-paying companies that join us, and we also created something called the Ag Systems Advisory Board to sort of welcome other sort of ag professionals, whether they be anybody who really represents the stakeholder community that we want to work with, that also help to bring their voice and guide the center. So I won't talk. I'm going to focus today on research, but I'm happy to share with you any of the other kinds of activities that we participate in as well. So I thought I would say you probably have a fairly similar graphic. I tried to shrink some of these slides down, is just thinking about making a farm of the future that looks much busier. We posited and look at the opportunity to build integrated systems. I'll sort of share with you the scope of our research, but really we're thinking about how do we capture the microclimate and spatially, temporally, and compositionally map heterogeneous stresses. So we think about that. We were talking, Deepak and I were talking about that earlier today. How do we get at all sorts of different types of stressors or targets that we want to measure, and how do we understand those with a different kind of spatial resolution than perhaps we have today, as well as temporally, how do we capture them within a growing season. So ultimately, we want to bring all these pieces together to control the farm. So we take this picture. Now we become scientists and engineers here, where we want to take this picture and we think about how to organize the work that we do. And so within our center, we have 3 research thrusts. Those research thrusts are, one is in agricultural sensor systems. So these depictions of color-coded things are supposed to represent sensors. I'll introduce you and focus on those today. Some of those will be operating on leaves. Some of those will be embedded in the soil. And so I'll introduce you today in this space of sensor systems, where the idea is, we want to embed sensors within the soil, on the leaves, to really capture the climate in which they're working on, to understand the plant themselves. Part of those sensor systems includes introducing or using robotics in addition to existing farming equipment, where we can actually, as a way to help to collect the signals that we want, as well as directly image the field. And so that's all in our first thrust. And then we think about our second thrust, is called communication and energy systems. How do we provide energy in some spaces where we might need often small amounts? And also, how do we take advantage or develop communication technologies or ways to get the signals out? And so that was certainly our conversation earlier today, where our colleagues are looking at how do we take the data from the sensors, get it out to robots or to existing farming machinery to be able to do some computation at the edge, and then to be able to get the data all the way out to the cloud. And then our third thrust is on agricultural response systems. How do we take all the kinds of data that may be heterogeneous? Again, this is where the spatial, temporal, and compositional components come together. How do we fuse all of that data together? How do we learn from that data, and then provide provide a set of controls so that you can provide recommendations to the farmer, so that they can sort of come full circle and act on that data and just make appropriate actions for their field. So that's the way that we try and think about sort of translating this picture here to the actual kinds of work that our colleagues all do within the center. So I thought I would share some faces. You probably, I know in different components, may know some of them here. So these are our 3 thrusts. And so you might see many colleagues I know. Tony Vine, that some of you guys know. I know you know perhaps David Love and Jim Krogmeyer over at Purdue, maybe some other folks as well that are within our center. That's just based on some of the conversations I've already had today, but where we really bring together expertise within the center in agronomy, agricultural engineering and economics, environmental science, and then the science and engineering side of both the physical and the cyber side of the systems that we're trying to develop. And so we look at really bringing together all of these folks who are working together in various forms to do the work that we want within the center. And so I figured, well, not just the faculty, we're all not so interesting. Perhaps sometimes it's better to tell the story and you can see all the faces of the students. So probably similar to you, we hold an annual meeting every year. We rotate amongst our different campuses, so we get to learn about the different environments and different cropping systems within our center. And so if we really try and count everybody, the last count we had was 254 members, but that includes all of the kinds of postdocs and students who participate in the center, teachers, faculty, and staff, as well as all of our advisory boards and deans that participate within the center. So one of the things that we think about as being different that really motivates some of our research, probably similar to you as well, is thinking about the technologies that we're trying to develop within each of the thrusts, but not that those technologies might not exist already in some form, but they don't. If you said, if I gave you a sensor, you say, well, I can go buy a sensor, right? But we really think about and are driven by how do we develop technologies that speak to the agricultural specific use case. And so that really means something different for IoT technologies than you might, it's not, that might not exist currently. And so we really think about the scale of agriculture, right? Particularly when we think about, crops. We also think about the environment in which the technologies have to work. And then we also think about the socioeconomics, right? That, it's not healthcare, right? It's going to be, we're going to have to think about, how do we meet the needs of farmers and having them willing to adopt the kinds of technologies that we would develop. So that's the way that we think about it. It'll drive a lot of the kinds of decision processes that we make. For example, when we look at building sensors, environmental and soil sensors, but if you look at it, they have to be low in cost. You'll see almost all the first thing we think about is that they're biodegradable. We're going to think about sensors that we can deploy and we're not going to go back and get. So we're not going, so it's a real driving force for a lot of the way that we think within the center. I'll introduce you a little bit briefly to some of the work that we're doing in robotics, often in the context of how it works with some of the sensors that we're deploying. So I could tell you sort of one good consistent story, not every story that we have within the center, so that you walk away with something at some level other than a high level. And so I won't talk as much today about some of the work on communications and energy systems, but I'll speak a little bit on the energy side, some battery technology that we're working on. But and I'm happy to introduce or answer within the capabilities that I have to answer any questions that you might have within the work that we're doing in looking at both energy and communications technologies, again, specific to their use in agriculture. And then also on the data side in our work to try and develop models based on the data, if we can bring the data together, fuse the data together, and then how do we develop models, but ones that are biophysically meaningful and not out in left field somehow. And then how do we develop this interface that will actually come back to interface with the end user. So within the center, so this is true for all NSF engineering research centers. We have to have something called test beds. So this is a little bit where that language comes from. We chose 2 test beds within our work on crops. One is developing integrated systems for precision farming of row crops, and the other is for tree crops. And so we think about, when can you use the same kind of technology, when can't you use the same kind of technology, because the different types of cropping systems will have different requirements. And so we thought it was an interesting way to challenge ourselves as we were trying to develop the work within the center to speak to, sort of broad classes of cropping systems, and of course that are important to farming. One thing that we did in recent time within the center in the last just over year plus is that we developed something that we called joint ops or joint operations. We did it because you'll see that as we look at all the different technologies across the center that exist within each of the thrusts, to be able to build integrated systems, we have to be able to bring and have a forum to bring all of those technologies together. Often that work happens within the research and education centers that are part of extension around the campuses of Purdue, UF, and Merced. Merced has now also recently received a land grant designation. And then we also work with other industry and regional fields. So, we're happy. We frequently travel from Penn to someplace else, but actually within, obviously, Pennsylvania, there's lots of opportunities as well. But what I thought I would introduce you to just these ideas here between that joint ops. It gives us a way in a construct to bring our technologies together. It's also one where we chose to do it around what we thought were important problems in agriculture as we thought about the needs that we want. So one joint op is on integrated systems to optimize nitrogen application in row crops. The other one in row crops that we just recently added is number 3, which is integrated systems to mitigate disease and pests. And so we think about where some of the guidance we're getting from our advisory board members and things that we know ourselves, we've added some of these activities. And then we also have a joint op on integrated systems to optimize water use in tree crops. This one is dominated by the work on the West Coast in Merced, where you can imagine how important the concerns over water are. So today I thought in telling you one story, I'm going to introduce you also, to be honest, to the part that I know the best, which connects to sensor systems. And so I'm going to introduce you to what we think of as sort of emerging technologies. There are sensors that we use within the center that are off the shelf or things that are one step away from off the shelf that I'm going to try and introduce you to what we think of as sort of a different approach in terms of introducing sensors. So I'm going to introduce you to 2 types of sensors. One that we introduce as leaf sensors, where mostly starting with that to introduce them in things like orchards, although we'll put them on corn stalks too. And then I'll also introduce you to the example of subsurface soil sensors. And in particular, we've started our work there with row crops and looking at basically being able to introduce sensors either up above the surface or down below the surface to really get the environmental and soil characteristics of the plants. And so we think about these sensors. I'll introduce you to both of those so that you can take a look at the details of them as well. But we think about how do we capture those signals that we get. The ones on leaf sensors are all optical. So we can use light. We can use camera systems and imaging systems to be able to capture their signals. Those can be deployed on robots. But we also look at existing farming infrastructure because there's lots of opportunities and power and things that are navigating through the farm. So we want to, there's no reason not to take advantage of those platforms in many cases. And then I'll introduce you to the subsurface soil sensors, and those are all operating in the RF. And I'll introduce you to some of the work that we've been doing there as well. So as we were looking at plant sensors, for example, I think, was it Matt said, well, most people just clip something on a leaf, right? And that's right. And so if we looked at what was in the literature, we looked at things that look like things you might clip onto a leaf. But one thing that you notice about all of the 4 examples, whether they're commercial or ones that you find in the literature, is that they often have a wire hanging off the back end of them. And so we really think that many of them are battery powered. They're a little bit more expensive, even if they're not quite as expensive as some kinds of agricultural sensors. And we think that really limits, of course, the number of sensors that you can deploy per acre, both because of the cost and because somewhere you have to connect them, right, someplace. So one of the things that we were interested in is how do we have sensors that are completely passive? You may have some trade-off in performance, right, for that, but how do we do this where we could make sensors that we could really deploy? They could be super cheap at less than a cent per sensor. And then you could think about, well, what if I wanted to put a sensor per every plant, right? And so we think about the scaling here to be able to put, if you wanted to, I don't know if we need to, right? That's still a fundamental question that we're trying to understand. Well, but, if I wanted to, I could put like 10 to the 5 sensors per acre, right? And that sort of would be at kind of plant level. And that would be, equivalent to some sensors that you today might have, $1,000 for one sensor, right? I could put instead 10 to the 5 at much cheaper. So we'll see how that goes. But in order for us to do this, we want to deploy sensors that we're never going back to pick up, right? Could you imagine, right? You're not going to go back and get those. And so we think about sensors that have to, in addition to being cheap, that are completely biodegradable. And we're not trying to power them, right? They're going to be completely passive. And so the idea behind what we've been trying to do, and it's really brought together a whole group of us, is to build sensors that basically just change color, okay, based on a target of interest. So what it does is that it combines an example of what's known as an optical metasurface, something that's just a highly reflective surface, but the color that you get that's reflected back depends on the refractive index of its environment. And what we do is that we put them on or embed them, on the surface or embed them within a surface that is often an adaptive polymer, a material that gives us the specificity to a target of interest. And as it uptakes something, it'll change its refractive index, and then it'll cause this color to change. And so I'm going to show you that in just a moment. This is an example on a leaf. Right now, we actually make them fairly big. It's not hard for us to do. You'll see we're developing fabrication processes to do that. Ultimately, I think we can make them a lot smaller. Right, I mean, in practice, we want to think about deploying them more like you would seed, for example, or fertilizer in a way that you could distribute them. And so, well, it'll just make my job easier because I won't have to make as many. Right? If we can scale up the fabrication, you can just cut these up. And we think about how to do this. We've started by looking at things like water stress. We've started some work on looking at temperature of the leaves, but ones where we're also developing some materials, for example, to recognize toxins, so that you can, sort of build a polymer that'll recognize a particular toxin. We've started with aflatoxin, but, things like that, and volatile organic compounds. These are the kinds of things with these kinds of sensors that we think that we'll be able to target. So as I mentioned a little bit just before, is that the idea is that you have a sensor, it's on your surface, and you could have light that's either coming from sunlight or light, for example, that you actually introduce a light source. I'm sure introducing a light source will sort of gives us a little bit more flexibility. I'll say that as we go through, we think about not just looking at frequency or color, as well as amplitude, but also looking at things like polarization control and putting sort of some of the optical requirements on the measurement system itself. But what we have here, for example, is that you're just looking at the light that's reflected back from the system, and as you have some kind of change in refractive index of the material that's shown in gray, then the color that you see reflected will change in color. We like this because these are based on what you think of as structural color, a little bit more like the leaves of a butterfly, and those are very robust. Versus, for example, working with pigments where pigments can get bleached, for example, over time. So as much as I personally have spent lots of my time studying different colorants or pigments over time, we didn't think it was the right choice for this application space. So what we're looking at, and you'll see just as we design these sensors, is that we look at, if you had the line shape shown by the dashed red line, the solid red line here, it's pretty broad. We'd rather have things that look like the filled in yellow shape, right? Something that's much narrower, so that if something shifts in frequency, it's much easier to tell the difference between the two narrow spectral features than the two broad spectral features. So that's part of the things that we think about in the design of the sensor, is how do we make these line shapes skinny? It's what's known as a quality factor, or what's Q factor. And so if they're skinny, then the Q factor is a big number. So that's something that we do in the design, and then we look at also designing the device so that it's, the response causes a larger frequency shift. So some of that's, we work on in time. Some of it you'll see here, and some of it I'll say that's, part of the design process that we're working on. So we said that it had speed. Go ahead.
Can I ask a question? So if I want to sense a different parameter, then all I need to do is to change the hydrogel?
Yeah, you need to just change the polymer. Yeah. I mean, some of them can have responses to more than one thing. So we also do think about how do you, often things respond to temperature, right? Yeah. So how do we integrate temperature, for example, and moisture? Or right now we're making things specifically for an aflatoxin molecule, right? So we think about how do you use, the one thing that chemistry is good at is specificity, like all the lock and key things you think about as a high level. Yeah.
How do you read and react? I mean, they're not sending you signals. You fly a drone over and
we
somehow...
do. That's right. So So the one thing here is that you would be, as you'd have to either fly a drone over it. I'll show you some examples of some things, or just on cameras that are in existing farming, or that you could put on existing farming infrastructure. Yeah. Yeah, so you have to be able to read these optically.
Can I have different parts of the polymer react to different things? Like how small can this be?
You could make them, I mean, for us to make things small is not hard. That's where I spend more of my career than this is, so, but yeah, so you can make things, or you could have different patches, that would allow you to do things in like what people think of as array-based sensing, like noses and things like that. So you could do that. The other thing is that we can divide the spectral space. So what we vision is having buckets where, this sensor operates and it'll shift within this so many nanometers, and then in a separate spectral range, we'll have something that'll sense for a different target of interest.
So if you're doing 100,000 plants per acre, which, as you said, that may not need that many, how do you stick these things on the leaves?
Yeah, so this is something, right now I'll show you how we design the material so that it sticks to the leaves. But what I'll tell you is, what we haven't done yet is ultimately I think we're going to make this smaller. And we'd love to do is to think about how do we do it like you deploy seed or fertilizer. I was sitting there looking at, these controlled release fertilizers, and I was thinking, a sensor that size would be fine. The catch that we've been looking at, and to be honest, has changed over the course of time, I think, in our thinking is, if you look at big platform aerial robots, they fly at like 40 meters. It's a little bit far, right, if you're going to want to measure something small, so then you're forced to make the sensor large, right? And I don't think we really want to do that, right, because it covers then more of the leaf, and you worry about what you, do you want to cover more of the leaf or not? So the way that we'd love to make them small so that you could deploy them, if I were to make them 2 or 3 millimeters on a side, that would be similar to, some of these kinds of.
I mean, you're gonna stick them on a seed and somehow it comes out on the leaf and you can.
No, you could, I would imagine, I'm not sure the word spray is the right choice, but you disperse them the way that you would. We would love to do it using kinds of equipment people are used to using already and just fill it with a different bucket of stuff.
Okay.
Yeah.
Would it be possible to use a drone to just
Yeah,
spread it
yeah,
over
this
the
is
field?
actually one of the things that we thought about was, having the drones carry payloads themselves.
Like,
You can imagine, though, the drones right now, they don't fly for very long, right? One of the things so I'm not, if you add more payload, but if you were doing something that you needed to be targeted about, where you knew there was something, that's the way I think that you would take advantage of a drone to be able to do that.
Also,
Does it have to?
if you just blow them out there, a lot of them will have to ground.
Yes.
And so then if you're taking pictures early on, they're gonna give a very different reading than what's on the plan.
I agree with that. Yeah, so you'll see that one of the things, too, is that I think, ultimately combining imaging of, it's not like you just get a projection of everything that's below you, but combining imaging so that you actually, that you have a sense of what is on the leaf versus the ground, I think is going to be important for us. Look, these are unsolved for us, I'll completely, but I agree that's something that we think about is how do you do that, and how do you, we may have to look at how we be creative and what is actually responsive in one case and not the other. Yeah.
This is completely speculative, but
Yeah.
I would think that being able to create a sensor that can do all this and be biodegradable and be low cost and be passive
Yeah.
is a much harder challenge than actually figuring out how to get it out on the leaves.
Right.
I mean, it's not trivial,
Right. It's not
but
trivial.
I think that's a solvable
Yeah.
problem, or at least we know how to do it with today's technology.
Yeah, I agree. I think that part is solvable, and I'll tell you how far we've gotten on the part that we're spending our time trying to figure out. So this is actually work from my own lab. So we spend time we work on a lot of small particulate materials. People call them nanoparticles or nanocrystals. Here I'll talk only about, I'll introduce you to examples of titania, so dielectric materials, even though we love metals and semiconductors and all sorts of things. But one of the things that we've spent a lot of time doing are creating these optical metasurfaces using imprint technology. And one of the things that we wanted to do here was to, instead of using our commercial imprint tool, we built our own to really allow us to scale this and to not use. Conventional ones are often in like your Beckman Center, right, where you require resist. We didn't want to use any of those kinds of consumables. And so what we have is these titania particles that are in water. For anyone who doesn't know, titania is like what's in your sunscreen, for example, okay? And so we chose it because it's not toxic. We're not worried about introducing titania. What we do is we create a template, and then we just literally press into the liquid, and it creates the structure that we want. And so just as two examples here, you can see we were creating these little pillar structures on the surface. I'll also describe us having pillars and leaving behind what we call a residual layer, where there's some layer in between. So it can be pressed down so there's nothing between the pillars, or we can leave a layer underneath. The advantage of leaving the layer underneath is it creates for us what's known as an optical waveguide. It actually is advantageous in the design of the sensor, which I'll introduce in a moment. We've started by doing this. You can see this is sort of a square inch kind of area. So even in our lab-based early generation ones, we've now been making new generations of these things. We can just, it's called imprinting. It's like embossing, right? Imprint onto the surface, and we can do this over a fairly large area. When we say fairly large area, there's nothing that prevents you from scaling this up further commercially. It's just that to buy a commercial stamp is like $20,000, and so since we want to go through changing designs, we don't do $20,000 a piece. We do ones that we can make ourselves, so we sort of stop at about a square inch. But there's nothing that prevents you fundamentally from scaling up the process further. And you can do this. It's all done at room temperature, and so you can do this on rigid substrates or polymer substrates. And so you can print on lots of things. What we've done is we can control this geometry by just controlling the initial template. We can also, both in the dimensions of the pillar structures, or it doesn't have to be round pillars. We can also control how high they are by controlling the height of that template. That's the difference between blue and red here, and by controlling how many particles that we have as a concentration in the dispersion. So we can control the height of these pillars, and then we can apply pressure, and depending upon how much pressure we have, we can either have no residual layer here or intentionally leave behind this residual layer underneath. And so the reason why is that if you just compare the green and this pink curve here, you'll see this pink curve here starts to show these nice sharp features. And so if anyone's a photonics aficionado, these are known as quasi-guided modes, and they give these higher Q resonances. So we've been looking at designs of the device that give us these sort of sharper features. So we have to marry this optical surface that's highly reflective with something that allows the sensor to both stick to the leaf surface as well as a layer that gives us that adaptive polymer that's going to be sensitive to a target of interest. So what we've started with, for example, is we've been working with chitosan, which is a natural biopolymer that is sensitive to water, to moisture. What we've been doing is that we've been taking it and mixing it with chitosan's a little brittle, so we mix it with a little bit of glycerol, and it allows us to mold these and create these substrates. And what we do is we mold them onto a patterned surface, and that patterned surface, if anyone knows the gecko, that's always the bio-example of choice, it gives us sort of a structural topology that then provides for very good van der Waals interactions with surfaces to give us adhesion to the leaves. So for example, these are some peel tests. And so if we put this sensor, it's pretty similar to what it looks like on another kind of polymer surface. Perhaps doesn't adhere as well as it does to a glass surface, but we can get them to adhere to the leaves. You can see there's a sensor here. We can roll the leaf around and the sensor stays. The nice thing about the chitosan and glycerol here is that it's better than other polymers in allowing for the diffusion of water, for example, or moisture through the material. So it allows us to sort of take up this water and then give us you'll see in another slide, some response in the sensor. And so this is some work we did out at Morsad, just looking at and putting these sensors on different plants like citrus and almond and things like that. So we had to characterize these materials. We first, of course, start in the lab-based environment. We just had some sensors on glass, and we just put different liquids of various refractive indices, just to give you a sense. If you change the refractive index of the liquid, you'll see these peaks shift. They also do diminish in intensity, which is not something we want, so we are working on designs to limit that. But it gives us, we can control whether we have one peak or two for some designs, but we can get pretty good change in the color that you see that comes from a change in the refractive index. We then took ones where we took this surface and we put it on our chitosan glycerol surface. And then if we just look at the relative humidity and its response to relative humidity, the relative humidity won't change the refractive index of air by any appreciable amount. But the relative humidity will get taken up by the chitosan here. And so you can see, we just watched, and you can see this peak shift as we look at different relative humidities, for example, between about 10 and about 80%. And so you could see the spectral change that would occur as you look at just the pickup of the water from the environment in the chitosan. So we've started to look at these outside, and I'll just give you, this is sort of for us where we're at now and trying to make a number of these now and scale up our fabrication and field testing. So my student Chavez went out and took a dozen or so sensors to California, and he mounted them on the leaf. So the one, there's some good, I'll be very honest, some good and bad in the experiment. The good part is that so you could easily, this is a handheld spectrometer that one of our colleagues had. We could easily see the color and the reflectance of the system. We looked at it, and the relative humidity outside changed by very much, but you see that this didn't change very much, which is good because we don't want, this is varying the relative humidity of the environment, but this chitosan is now not available to see the relative humidity from the environment because it's on the leaf. The only problem was they didn't water in the time period we were there, and there was no rain in that season when we were in California. So you'll also notice that it didn't change very much. So what we're looking to do is in our next trials, we'll actually make sure we time it with intentional watering to see whether we can pick up some of those signals. But we were certainly able to, this is sort of our starts at being able to measure these out in the environment, for example. And I'll just sort of finish this story by saying there are pieces you asked, how do you measure these? We look at camera systems, and some of the works in the Kumar and Kopal groups at Penn in Florida are working together to look at different platforms and looking at different hyperspectral imaging systems as a way to go in and measure hyperspectral and RGB, for example, to basically be able to identify. So we have sensors deployed on leaves, and they're able to go in and use algorithms to identify the object of interest. And so they can then find the sensor, and then they can look and see what color the sensor is. And so that's sort of the stage where we're at, is in developing some of those so that you don't look at everything that's in your field of view, but you use some of the algorithms that they're developing to go in and focus on the target of interest.
How dependent do you think this is going to be on hyperspectral as opposed to RGB? Because hyperspectral gets expensive.
Yep.
I don't think it's widely used in production ag.
Yeah, so
sensors obviously are cheap.
So we can certainly, the hyperspectral is certainly easier. I think what we have to look at is the balance between, again, I think it's going to be a balance between lighting systems, the design of the sensor. Are we allowed, if we open ourselves, I'll be honest, we're looking at trade-offs to introduce polarization control and selectivity as a way to be able to pick out signals. So I think it depends, there'll be different ways to push on this problem and see, where do we, is one really a limitation from the others? But these guys are trying to look at building some simple systems that are off, things based on cameras that are available commercially that are used in ag.
I can imagine RGB is very sensitive to bright light. If you
Yeah,
have a very
right.
bright day.
Yeah, so I think we're going to have to see whether or not, what are the trade-offs that we're going to have to make, and which is the way to do it, somewhere match between cost effectively and reliably. Yeah, so I think that's still in our future. So I just thought I would introduce you as well to, I was talking with Alani earlier today, but we have some of the work that's being done in the Kumar, Chowdhury, and Asani groups, which is also to look at these are examples of introducing different LiDAR and RGB systems and stuff like that to also navigate through, for example, orchards. They do also navigate through forests because it's far less predictable, so it's a good challenge for them. So they do run themselves through forests, but here they're using their semantic SLAM to basically be able to go and identify trees, learn how to navigate through them. And then as they go through, here's an example in a forest where they're trying to measure the diameter of trees as they traverse through the forest. This is an example of an orchard where they're doing something similar out in California at Merced. So they've taken these kinds of optical systems and either put them on aerial robots. This one's on a cart that they can drag through with a tractor. It's always fun to see the guy from Penn driving a tractor just looks so happy. They actually have this, if anyone's interested. They've also generated about 10 hours worth of data, and so they've shared that data open source. They've distributed the data as public data, and then they also have some of the work they've done on the segmentation and stuff like that are also available open source. So if anyone's interested, they recently put together this website here, which I think will take you to everything. And then they also have a paper on this that's on the archives as well. All right, so from above the soil surface, I'm going to just take you a little bit below the soil surface and sort of finish a little bit with these soil sensors. And we've started with moisture, again, very similar to the above soil. Often things like tensiometers obviously are wired. You can't afford to have too many of them. These are this is the simple Arduino cheapo sensor, which lasts today but not tomorrow. We use them in outreach. They break every other time, right? I use them in my class. I think we just know that we're just going to replenish their supply. And then these are some other larger capacitive moisture sensors. We visited Florida, and the guy came out and showed me was holding his capacitive moisture sensor, and I thought, my heavens, the thing is huge. And he's like, each one of these is $2,000. So we're certainly highly motivated to think about alternatives. And so it's very similar to the motivation that we have behind the leaf sensors as well. So this brings together, again, a number of research groups at Penn, Purdue, and UF. And the idea behind it is to, again, we want to be able to develop these sensors that we can deploy below the soil surface. We do not want to go back and get them. So again, it requires us to look at a much more limited material set from which we can build the devices and look at sort of wireless sensing platforms. So the idea behind these are either we have two kinds. One is completely passive, where there's an antenna, a sensor, and we do look at putting a small silicon chip on the sensor that serves as a tank circuit. I'll show you that in the next slide. We do have some work that I'll finish with in showing you batteries, and those batteries are designed also to be biodegradable, again, very limiting its material set. But if we wanted to do something that would allow some data logging or allow for some greater range of communication, then we'll have to look at incorporating these. But the idea behind these is to allow us to measure moisture, pH, nutrients, and so we have a couple of things working on how are we going to measure each of these different kinds of targets. Okay.
So Supratik Guha at Chicago has this project called Thoreau. You might be aware of it.
Supratik extremely well, but
sorry?
Supratik and I used to work together, so at IBM, yeah.
So he's been working on these underground soil sensor boxes. You might be.
I've seen some of it, but not so much of it. So yeah.
So I think one difference is that they are actually using a remote, basically they're using wireless to send the data back.
Yeah.
And they've done both LoRa and, forget the name of the second technology, it's a commercial one. And they're able to get data over a couple of kilometers or 3 kilometers.
Yeah.
So it doesn't have to be done.
So we do it in two steps, I guess is one way to think about it, is how do we pick up the signals below where there's, the sensor's not as sophisticated, right? It's not carrying as much capability so that we can pick up the signals. And then within the field, we have, some version of a communication. So we have LoRa or something else.
Yeah. But they actually have a battery. You do have a battery too, I guess.
Well, let me show you, but we don't have much battery. There's a small amount of power that we will look at introducing, and but it's probably a little bit different than the I will call.
So they said they can last over 3 or 4 years with a W.
Yeah. Okay.
It has these big boxes.
No, they're about this big. The box is only about this big. It's sealed in the battery.
Okay, so
inside.
I guess what I should have done is put the picture, and we have an image with a size of a quarter. So these sensors are closer to the size of a quarter and very flat.
Here's a much bigger.
Yeah.
And is this like a RFID-like sensor that it reflects the signal?
Yeah, so the idea behind it is that we send in multiple frequencies, and then you'll get a reflected signal back, but most of them will be reflected in short time, but then depending upon the resonance of this, we have this tank circuit here that then delays the signal of the frequency that we're interested in measuring. And so that, again, the way that these work is very much like the way that you think about the colorimetric sensors working. It's just that color or frequency is changing in the RF domain instead of in the optical domain.
So that sensor, just presumably the one that you can see on the left there, is just for moisture. And is that completely passive? Does that not need a battery?
Yeah, so this one is completely passive. The first ones we have made are based on moisture. What I'm going to show you today is based on moisture. But the same material set that we're looking at to integrate for the leaf sensors to measure different targets, we're using the same approaches. I view these as platforms, after which I can change one material. I can change design to split up frequency domain, but then I have different materials that give us specificity to different targets of interest.
How deep can you put that and still energize it?
Yeah, so I think I have it on the next slide, some calculations. Right now we've started small. I think we're at 5 centimeters, but it's some.
What's the frequency that you're using?
It's around 900 megahertz in the ISM band. Yeah, it's coming up on the next slides. That's okay. I can go faster on the next slides then. So that's what we're looking at doing again within the constraints of the material set that we want to work on. So this is an example of again a simple storage tank circuit that we use to delay the signal of interest. The first ones are really simple, where we have just metallized interdigitated fingers within the sensor, and then we're looking at the take up by moisture that the field it feels around it, either in the soil or within the substrate. You'll see that we've intentionally designed substrates that will allow us to take up some moisture that's coming up. That gives us a capacitance change. But we're looking at things that operate around 900 megahertz. And so, and within this frequency band to look at changes in capacitance of these kinds of levels. So just to show you what does it mean for us is that to make these really cheaply, we're using things like screen printing, right? Like what you make your T-shirt out of. So, I think probably, different in the kinds of cost scale we might be at compared to what Supratic is doing. And I think all of those have a place, by the way, that, just a question of, and how many do you want to put, and where do you want to put what kinds of sensors? So I think that, it'll take all of us to do this. But if you look at it, so we started with screen printing commercial silver inks. I didn't put it in the slides. Silver is not the favorite material for biocompatibility. So in my group, I said we work on particles, and particles of many kinds. We're just finishing some work on copper. Copper is a much more acceptable material system, and so copper will biodegrade, and so we can do some of the same things out of copper. But we had to develop a process that would allow us to do the whole process at room temperature, because we didn't want to. A lot of these kinds of inks you have to heat up. And what you'll see is that the substrates that we're trying to do this on are paper, right, or cardstock. One of the things in the work that my colleagues in the Turner group did was to look at screen printing on different substrates to get the kinds of lines that you want. Things that were a little rougher, like cardstock itself, was not so good. They've been infilling it with cellulose, which is also biodegradable, and that gives us nice-looking characteristics. And then this is some of the first work they did on testing these materials. So they printed these kinds of circuits. We have within a probe station, we can infill it with soil. We can control the moisture of the soil by adding water. They did this externally to connect it to the tank circuit, but you could see frequency shifts that depended on the amount of water that operated within this frequency range. And then more recently, just so that we could get something out of into the field, this is not the way that we really want to communicate, but they built a larger inductive antenna. And so by using some inductance sensing, we were able to take these out into the field to see how the rest of the sensor would behave, with all the materials that we're trying to introduce. So we could see that, depending upon how much, this was done in the lab, where we could see, depending upon how much water we added and soaked, you could see a change in capacitance. That change in capacitance changes the resonance frequency, and that's what we can measure. And you can see the sort of time scales of minutes, which for the frequency at which you're going to go measure out in the field. This is way faster than we need for the application in agriculture. And so they've taken sensors. They had taken, I think the number was 7 on the first time out to Purdue. They buried the sensors in soil. This is what the sensor looked like after about 4 or 5 days out in the soil. And they went through and had some sensors at different depths. They could see for the shallower ones some small changes. It happened to really rain, and the moisture level in the soil didn't change very much over the time that they were there. So, we of course will be looking again. So for a very small change in the amount of moisture within the soil, because it had rained just beforehand, we didn't necessarily see so much of a change in the sensors, but of course needed the commercial sensor wasn't seeing very much either. But we're seeing that we can get signal from these things within the soil over a number of days, and so we were able to look at them and retrieve them and analyze them afterwards. So this is something that we continue to work on and to look at. We'll be swapping out this design shortly as well. So I think I'll finish with just saying, I introduced you to the idea that we also had some that required, we could think about introducing batteries. So my colleague, Mark Allen, and his group has been looking at what we call as biodegradable zinc air batteries. So it really is just a stack where it involves some natural waxes. That's the packaging material, which looks like this yellow color. And then they stack, if you look here, they have a gel electrolyte, I think of zinc, and then a sort of air cathode. It's usually a carbon paper that is used to build and complete the cell. And then they've looked at, looking at how long it operates for example, out in the soil. They actually have some recent measurements where we can also get the sensor to communicate with other with the battery. We have it connecting with some of the other communication technologies out at Purdue. But you can see that we can get the sensor to deliver power, small amounts of power over sort of kind of months kind of time scales. It also depends on the size of the sensor of the battery that you make. But you can see it's sort of components that you see here. I dare say that they call it a corn cell, which I find because it happens by the time you finish packaging it. So this is the corn, and that's the cell. But we are looking at how do we continue to develop these materials as a way to have things that are entirely biodegradable, but deliver the small amounts of power that we might want to add more function to some of the sensors, especially if you do things like electrochemical sensors that are going to need some power. So I think I'm getting close. I'll just say, I have 2 slides. I'll just say this is some of the work from Dave Capillari's lab at Purdue. I knew that you guys were also looking at things of how you can control and collect samples. They've been developing this Jackal-based platform with this end effector to be able to go in and sample parts of leaves. They've also instrumented it with a number of LiDAR and RGB cameras that allow them to also go in and visualize, to walk between the rows of corn and to be able to visualize and image for example, to measure the width of the stalk and things like that. I thought I'd finish just with the one example here where they've been using it to know where, if they were going to take a sample, so that they've been interested in measuring closer to the collar. So what they do, they've developed algorithms and to be able to go in and take their images and then to be able to identify the leaf. And then they can also, I have other ones where they can then identify the collar, and then they can then pick and then take this nichrome wire and cut and sample the leaf and then take it back. And so this is just some of the examples of his work as well, just to give you a sense of where we go from the sensors out to other things. So one step further along the chain of using some of the robots within the center. So with that, I'll stop and be happy to take any questions. I think I've kind of said this the sort of motto of our center here. Maybe I'll stop without saying any of these words, but I'll be happy to take any questions that you might have.
So, in general, what are the strategies you are thinking about in terms of how to handle the data that you're going to be generating from these sensors?
Yeah, so you mean once we get the data out to the cloud? Yeah, so we have, certainly colleagues who are looking at how do we share. I love the teaching me the word interoperability of this data, but do you mean so we have efforts of how do you take all these data together and register and overlay them and to have data at different resolutions, different temporal resolutions, and so we have colleagues who are working on what they describe as sensor fusion technologies to basically be able to take these data and then merge them together and to overlay them to get a sort of consistent picture. So some of our colleagues, for example, at Merced have been doing this. They've been doing it with, anywhere from, satellite to robot to, other kinds of handheld kinds of data, and have been looking at some test examples, for example, on water. And that's only one measure, but they're looking at algorithms to be able to basically, build a complete picture from that. Depends on how far you're going to ask me to answer as to whether I'll be how well equipped, to be honest, that I'll be able to tell you more about the approach, the algorithms that they're using.
Yeah, no, because I feel like that is a common challenge in that.
It's a big part of the effort that it's certainly a part of the effort that a couple of our colleagues within the center who are working on how do we take all of these disparate kinds of data, especially if you let us introduce these new sensors that are going to be of a different, the quality of the data is going to be different. So it's certainly I think it's going to be one of the challenges for us to all work on. I think that, they've been building their techniques and, I don't even think they're ready for us yet, in some sense.
Can I follow up on that? So nature solves these problems with redundancy, right? So if you actually have enough density per unit of
Yeah.
the sensors distributed, you may be able to solve.
Yeah, this is exactly the argument. I think I was having this conversation earlier, that, what we think of as an opportunity, very different than the way, we find that, many people who work on sensors, they're looking at the one sensor, and what does the one sensor give you, and how do you, trust, rely, ground truth, agree. But I think we have a very different, I think of it as a very different approach, where we have numbers, right, and you have an opportunity, right? So yeah, I believe in redundancy, knowing it from a computing perspective, but I agree. So the question is, if you have so much data, how do you take and build, even if they're not, even if the quality of the data isn't as good, how do you take advantage of the power of the number of sensors? And I think that's a distinguishing feature, hopefully feature, of the technology that we're trying to look at, that we'll have here, that's perhaps a little bit different than the way that people have thought about it previously. Hopefully, maybe.
So you talked about using SLAM in that robot system, and you've been using drones as well. Have you working on localization of a machine in a field to identify which plant has a particular symptom or
Yes, so
characteristic or feature or something,
yeah.
to really do very precise geolocation?
yeah, so yes. So in particular, do you know Vijay Kumar? Or at least by
met him.
name? So him and Reza, they've actually, even before the center started, have worked on some of these kinds of ideas where at the same, some of the things they want to do is, as they go through, they'll count fruit. They looked at greening disease in oranges and things like that, so that you could go in and pick out and be able to, on the fly, be able to analyze some of the data and to pick out, where you have, concerns, right? And so that's something that they've been working on within their skill set.
Because one of the things I read somewhere on your website, I don't remember exactly where I read it, was this idea of managing fields plant by plant rather than region by
level of
region,
individual
acre by
plants.
acre.
Yeah.
And I actually saw some similar literature called Taylor's Granular Insights product area, which they talked about this as a long-term goal. And one of the things I don't know, and I really think the agronomist, I guess Nico just left, but David and Elhan may have, or Matt may have some insight into that, is whether that is a useful goal. Is it worthwhile in practice to develop the kind of engineering capability to manage fields and crops at the individual plant level rather than just over subsets of a field or something that Precision Ag does today?
But unless you really change how big the machines are or what they can deal with.
Yeah.
So
let's say you have a small machine,
you've got
that can go between
applicators that are 60 feet wide.
Right.
And maybe you can make every row do something different,
But forget the machines. Just imagine you have a very small machine or a team of very small machines.
Yes, it would. Like, that is the bottom line. But the problem over here is the bigger the plants, the more valuable they are. That, the value of managing it individually
individual
increases.
one.
So
Sure.
that would be my
Like for trees.
right. That would have been my answers. Is that so? It depends which crop, right? So
Yeah.
some of them are very high valued crops. You'd be happy to, it'll be effective, cost effective, time effective to do that. I think it's what I'm going to share with you, and I won't, in the sense of, so what we hear from even some of the industry members who we work with, like deer, think most of them are row crops. They still want to do it at the level of individual plants. And I think that, there are efforts too. We even have some folks who are working on spray systems where, you could potentially alter, how you manage what gets applied and where, and there are certainly things that are targeted. But it's interesting for me to hear that when I think, well, you're largely working on corn and sorghum, right? That you still think that that's what you want, right? And so it'll be interesting, I think, as we look at, I don't mean us, I mean all of us, right? Like technologically, where we end up is to, to see what really makes sense. Even though we could put sensors at that, even if we can, is it valuable for us to do? And I think that when we look at sort of the fundamental questions, those are some of the fundamental, when I talk to our colleagues who know far more about plants than me, right? We don't know the answer to these. And so I think some of it is what we'll just learn from that as well.
Well,
I just wanted to follow up on
You
that
disagree.
because-
I'm happy to have you disagree because I'll learn something.
No, I think it's an interesting question because obviously, we hear a lot from, the people in California. If you're doing wine grapes,
Yeah.
right, then it's worth having
Yeah.
a meter on each, especially high-end wine grapes. Each vine knowing exactly how much water it's getting, and they often will deliver water to individual
Right.
plants as well. But the issue for row crops is less about managing individual plants, and it's more about the fact that we always work on the central limit theorem, and we're looking at the average of hundreds or thousands of plants, but we don't know what the variance is like. And knowing that plant-to-plant variation across the field is very important for modeling yield, especially when you start pushing the boundaries of what's possible in terms of the plant being limited by fertilizer, by water, and things like that. So knowing what that distribution looks like at the individual plant level is very useful from a scientific point of view and from a decision agriculture point of view, even if we would never say, okay, this plant needs a bit more nitrogen than that one, because that's not going to work.
Yeah, that makes sense.
So I have a question for you. What if you could measure something different? Like if you could detect disease, right? Does it change the problem where then you just don't want it to spread, right? Especially since some things could be airborne, so you don't want to wait till, things, so that's, I wonder, I don't have the answer to, to these. I think they're more questions to see,
That's
then we
exactly
ask
what
a
I would
different
love
kind
to
of
hear.
question. Right.
I'd love to follow up with you about that because I just recently talked to some of the plant pathology colleagues of ours at the crop sciences department, and the way that they describe what they do, they basically have this pollen and spore collection stations they set up with certain intervals.
Yeah, our colleagues do too.
It is attached to a car battery and it has a sticky tape. So it basically sucks in air that sticks on a tape, and then they do counting of the, bad material on the tape.
Yeah.
There's got to be a better way to do this.
Right. Yeah, we've been talking. Our colleagues in Florida also have this, and are very interested in this question of, disease and pests and stuff like that. And so, but also they are looking at how do they look at spores and how do you characterize different kinds of spores. And then they're like, interested in spectroscopy, and they're like, well, I'm happy to help, but is this really what So it's interesting, I think, set of questions. So you disagreed. Tell me why.
I don't remember what I disagreed with.
Oh, okay. I'm happy to learn, so it's totally.
I was interested in the polymer that you use. For example, like alpha toxin. Obviously, it can be extrapolated if we're able to detect plant defense compounds. What is that process like in discovering or developing a polymer that will actually do that detection, so you can see it via light? I assume there's a lot of factors that go in, but what are some main factors that
So
go
the
into
main
that
thing
development?
they're using, have you heard of molecular imprint polymers?
A little bit.
Okay, so this is like making yourself the key, the lock for the key or whatever. I don't know which way you're saying, but it's like so they intentionally have a sort of surrogate that's very similar, and they make a polymer that is matched to that particular surrogate, and then they that's how they make this. So it's referred to as molecular imprint polymers. It has a lot to do with sort of matching the particular target's shape, but it doesn't only have to, a lot of these things, if you think about even how some of these like ion sensors and other things work, it's also about shape, it's about charge. So even the things that you don't think about, that's what you're using. That's also how, it's why you can distinguish, potassium and sodium with some, 5 orders of magnitude difference between there, right? So it has a lot to do with the kind of design of the pocket. The way is the simplest way, and so that's
probably right.
What's that?
The size of the molecule.
Yeah, it has to do with the molecule. Like the ones for ions often look like rings. Okay, they're something called crown ethers, for example, and so they have a certain size and charge, and so they'll fit one but not the other, right?
And so when you make those with the VOCs, does it change color by default in some sort of spectrum that's detectable? Or?
So the idea is that those materials, when they pick up the molecule of interest, it'll add material there, right? It'll change the refractive index, and then the optical surface will then change in response to the change in refractive index.
Thanks for clarifying.
Yeah, sure.
I have a question out of curiosity. I recently saw this self-drilling, planting, seed
Yes, I
planting.
did too.
Yeah? Do you think that would be a way to deploy your underground soil sensors?
So those were bigger. As I recall, they look like little spinners, right? They were a little bit like the maple leaf things that they would.
Yes.
I saw as spinners. So I think that there are other interesting ways to think about how you could get things that might, bury themselves in the soil. I did have a crazy idea with a friend of mine who's in chemistry at UCLA on how to do this. It's a little bit different than the exact spinner, but on ways. So I think that that's possible, but the way that we think about it now is to actually do it is to think about whether we could do it in the planting process, where you would use the same kind of existing, making sure that our sensors would work to be deployed like you would when you plant. And so you plant the seed, you plant a sensor. So, I'm happy to try and, I'm happy to think about sort of, out a little bit more out there kinds of ideas, but I at the same time, I think there may be ways for us to do that just using because those, if we're unless you're planting it at some point during the season when can't deploy that equipment, then, then I could imagine that you'd have to think about a different means of deployment than during the planting process itself.
The other thing I saw recently was this film-based solar panel that they were saying quite flexible and
you can make
biodegradable.
Yeah, biodegradable, that would be interesting. But certainly you can make flexible solar panels.
That would go with whatever.
That you could certainly deploy. The most I've said about it is a little bit more of what people think of as like crop sharing, whatever. So that you share the, space between center pivots and, so you could certainly, think about, we thought a little bit about deploying solar panels or solar cells. Things that are flexible, you can make them that are flexible. I don't know that you're going to yet. It's an area I know more well than some. I'm not sure you're going to necessarily get it out of material sets that you're going to think are, the question is, are they acceptable? Well, some of them have elements you might not choose. So, the ones that are getting a big hype in there right now, if anyone follows these metal halide perovskites, they have lead in them. So,
Oh, no.
Right, there we go. Yeah. I've spent a lot of my career working with cadmium and lead. If Moon Sub is still on here, he gets to work a lot with cadmium and lead. But yeah, there's, I think that's one of the things that there are alternatives, but I don't know how, even then, the whole cell requires, you have to build up the stack of electrodes and materials for injection of charge. So I'm not sure it's where I'd focus.
I think we should thank Cherie for a very good talk.